Good morning, everyone. So today I will present iodine-catalyzed thioglycosylation of indole and tryptophan-containing peptides with thioglycosides. So this topic today I will present iodine-catalyzed thioglycosylation. In this case, they have used the tryptophan-containing peptides and tryptophan with the different types of the thioglycosides. With the help of this iodine, molecular iodine they have taken, and they have taken the sugars like thiosugar, C1 thiosugar or C6 thiosugar they have taken in this case, and they did the reaction with the glycopeptides. Firstly, these indole thioglycosides. What is the use of these indole thioglycosides and from where we can extract these thioglycosides? Basically, these are different types of alkaloids which can be extracted from these Istis indigotica roots, which is generally originated from the Chinese. In China, this plant is generally found. And these indole thioglycosides represent a key structural motif in numerous natural and synthetic molecules exhibiting wide range of biological activities, like this kind of alkaloids having antiviral, anti-inflammatory, anti-cancer, antibacterial, antifungal, immunomodulatory, hepatoprotective, detoxifying, antipyretic kind of activities they are showing. So today we are discussing the indole thioglycoside representatives. Basically, these are some of the oxa glycosides. And here is 6 number. There is one example of thioglycoside. Another this 5 is another example of thioglycosides. So previous work, synthesis of indole thioglycosides. Previously also there are some reported methods in this case. For example, N-thioglycoside succinamide and this indole. So when this indole will react with the N-thioglycoside in the presence of catalytic amount of copper or TMSO triplet, that will provide this indole thioglycoside. Another method, reaction of indoles with selenosulfonyl glycosides in the presence of NBS. It can also give the indole thioglycoside. Next one, thioindolinins and bromo sugars. Basically here, indole have this thiol compound, thiol functionality, which undergo to the SN2 reaction with this sugar bromide and which will again give the indole thioglycoside. Another one, radical cyclization of 1-isocyano 2-steryl acetate with thiophenol. That will also provide the indole thioglycoside after radical cyclization. This will form as a indole and substituted thioglycoside unit. Another method is nickel catalyzed coupling of iodinated indoles with thiosugars. This thiosugar will couple with this iodinated indole in the presence of nickel, which will provides again indole thioglycoside. So these are some previously reported synthesis methods of the indole thioglycoside preparation. Now there are some drawbacks. There is limited substrate availability, the use of toxic reagent and low yields of these reactions, and the requirement for metal catalyst. So in these methods, there is use of metal catalyst. So there is scope of any other free metal catalyst method. So for that purpose, this work, they shown iodine catalyzed thioglycosylation for tryptophan modification in the absence of metal. Here they are using only molecular iodine. They are giving some 26 examples up to 97% yield. They are basically using the C6 sugar and other OH are protected by the OBN or OBZ groups, whatever the protecting groups they have taken. And the advantage of these methods are metal-free catalytic coupling reaction between indoles and thiosugars they have presented over here. So basically metal-free coupling reaction they have shown here. Then use of molecular iodine, which has low toxicity and unique properties that are comparable to those transition metals. So use of molecular iodine they have shown, and it has demonstrated remarkable catalytic efficiency. Now, optimization reaction conditions for this method. Here they have used 1A as indole, then 2A as a methyl glucopyronoside, and C6SH is there. In the presence of iodine, solvent, temperature, and time, they are getting this reaction at the C3 position of the indole. Now they first started with the 5 mole percent of iodine, DCM as a solvent, 80 degrees Celsius temperature. For 36 hours, they are getting some 19% of the yield. So according to this result, they modified their they varied their solvent scope like ethyl acetate, THF, 1,4-dioxane, DMF while keeping the other conditions as the same. In the case of dioxane, DMF and H2, there were no reaction. But when they tried the acetonitrile in 5 mole percent of the iodine and 80 degrees Celsius temperature, 36-hour reaction, they are getting some 36% of yield. Now they kept acetonitrile as a constant solvent and they wanted to vary the other conditions. For example, they kept acetonitrile as the same solvent and they tried this method in the case of microwave reactor. So in the case of microwave reactor, within 8 hours, that compound is decomposed. Both the starting materials were decomposed in this case. So again, they decreased some temperature, like 60 degrees Celsius. So they got some 21% of the yield. And after some time, they decreased the 50 degrees Celsius with 5 mole percent of the iodine. They got some 45% yield. Now, trial basis, they have again increased the percentage of this iodine, 8 mole percent. They are getting some 86% of the yield, which was good. So different catalytic percentage they have tried like 10 mole percent, 20 mole percent, but while increasing the catalyst percentage, they were decreasing the yield. So basically 8 mole percent was the perfect optimized condition for these reaction. So they tried this reaction in different kinds of substrates. These are some reaction scope of thio sugars. Now they tried some hexoses, some pentoses, and with different types of protecting groups also. Like this one is the glucose with protected the benzyl, which we have already discussed in the optimization condition. And here for scale-up reaction, they have tried 2 millimole of this indole derivative, and while scaling up, they are getting some 81% of the yield in 25 hours. Again, in the presence of glucose with the benzoyl protection, they are getting some 92% of the yield. Then benzyl protection in the case of galactose, they are getting some 67% of the yield. Benzyl protection with the mannose, 80% yield. And at the C1 sugar, like C6 sugar, we have seen. Now, in the case of C1 thio sugar, here also they are getting reaction at the C3 position and 75% of the yield. They tried some pentoses like alpha D arabinose and beta D arabinose and ribose sugar. They have tried in this case. There also they are getting some good yield, like 74%, like 77%. It is good yield with the same reaction conditions. Now reaction scope of unprotected sugar. Now unprotected indoles. Now sugar is done. So basically they wanted to see the effect on this reaction with the help of electron withdrawing or electron donating groups on the indole. They tried some electron withdrawing group like chloro or bromo, then electron donating groups like this OH or OMe in this case. But there are no such difference in the yield or difference in the reaction. They observed very good yield, like 90%, 97%, 80%, 97%, and 90%. So there are no such effect of these electron withdrawing and electron donating groups on the indoles. Then they have tried some unprotected indoles. For example, these OH or unprotected indoles. For example, these acid component on the indole. Here also they are getting some good yield, like 77% of the yield. Now iodine-catalyzed synthesis of thioglycopeptides. So now indole part is done. Now they optimize the conditions. They tried with the different types of substrates with different types of sugars and different types of indoles. Now they wanted to try the same method in the case of glycopeptide. For example, this tryptophan unit is there up to here. It is tryptophan unit and another amino acid they wanted to use and they wanted to try this reaction. So 4 and 2B they have taken. This AIM is different kinds of amino acids with the same reaction conditions. They have tried like glycine, tryptophan glycine, then tryptophan alanine, tryptophan valine, tryptophan leucine, tryptophan isoleucine, tryptophan phenylalanine, tryptophan, leucine, and glycine unit. So these are some glycopeptides they have tried, and they're getting like good yields, like 68%, 74%, 84%, 57%, 56% with the same reaction conditions. They're getting these different types of reaction with the different types of substrates. Now, synthesis of unprotected glycoamino acids. Now, in previous slide, we have discussed that they protected the amino acids and they tried the this reaction in case of protected amino acids. Now they wanted to try the same reaction with the unprotected glycoamino acids. So here, see, it is acid group is an unprotected one. So same reaction, same conditions they have tried in this case also. But unfortunately, they are getting very less yield. Less yield. It's like a 15% yield they got in this case. Again, in the substrate number 8, they have tried the same reaction. But in this case, there were no reaction. They are not getting here 9 as a compound. And 5D, where we discussed in the last slide, they are getting this 5D as a compound. So they tried some deprotection of these all functional groups, all protecting groups. So in the presence of AlCl3 HF5e, they deprotected this CBZ group and getting this NH2. And in the presence of lithium hydroxide, methanol, water, they are deprotecting this ester group into the acid and these benzyl groups. So they are getting here free protecting group free compound. Now all the things are done, like they have tried with the glycopeptides, they have tried with the different types of indoles, sugars. Now they wanted to see the mechanism of this method, so that they did some control experiments. In this control experiment, they have taken this 1A as an indole, 2B, which is a thio sugar, in the presence of iodine 8 mole%, acetonitrile, molecular microwave 50 degrees Celsius 13R. But here in this case, they did reaction with the nitrogen atmosphere. Initially, they are doing it at the open atmosphere, like in the presence of oxygen. Here, they tried it at the nitrogen atmosphere. So one result they are getting, like in this case, there is formation of 53% this disulfide linkage, and expected compound was only 12%. So on this reaction, by the result of this reaction, they were thinking maybe oxygen is also acting some role in this reaction, because in nitrogen atmosphere they are getting very less yield. Another control experiment they have tried, like 2B they have taken in the presence of iodine, same reaction condition they have used, but in this case they have not used the 1A like indole, and they tried this reaction. So 98% they are getting the 11. So by the second reaction, they are considering that this intermediate is forming within the reaction, because here also it is getting 98%. So it is there in the reaction. Disulfide linkage is there in the reaction. Now they mixed like 1A, this indole, 11, this compound, and or 2B. Maybe this also they can use, or this also they have used. Without iodine, they tried. So they wanted to, they were thinking like iodine is act as to prepare this disulfide linkage, and further reaction is going without iodine. Maybe it is the case they wanted to check. So they tried without iodine. So there were no reaction. That means iodine is not only for the forming of this disulfide linkage, but it have some other role in further reaction. So from these three results, they concluded that. Then fourth result, they have taken this 1A, then this one disulfide linkage, sugar, iodine 16 mole% they have taken, acetonitrile. So they are getting now 92% of the yield. So while considering these all four results, all four reactions, they given some possible mechanism. Here is the possible mechanism. First reaction, they are getting oxygen role. Second reaction, they are getting some disulfide linkage. Then third reaction, what is the role of the disulfide linkage? And fourth reaction, role of the iodine. So summarizing all the things in the possible mechanisms. So first iodine, which used to the form these disulfide linkage. So basically it's oxidation of this thiol sugar, which is forming this disulfide linkage. Then again, it is reacting with the molecular iodine. So forming this sulfonyl iodine, sulfinin iodine 12 as moiety, which undergoes to the electrophilic reaction with this indole, radioselective electrophilic reaction, because there is only formation at the compound at the C3 position here. So radioselective reaction with this 12. So there is formation of 3B as a possible compound, as final compound. So conclusion, developed an efficient and selective iodine-catalyzed thioglycosylation reaction for the functionalization of indole and tryptophan-containing peptides. This method expands the synthetic accessibility to broader range of S-linked glycopeptides. It demonstrates its applicability in the functionalization of complex peptide substrates. The high yields and mild reaction condition make this approach a valuable addition to the field of glycochemistry. Thank you.
Good presentation, Mahesh.
Yes.
How they are controlling this amide C2 and C3 position attack of nucleophile? Go in next slide. Here.
Okay, here you are
Some.
telling. So basically, whenever the indole reaction is happening, it is happening at the C3 position only because it is more nucleophilic.
Okay.
So in this case,
in that case, this is block.
Yes. So in this
that's
case,
why is happening is C1.
Yes,
But
C2 position.
C2 position, this position.
Yes.
And if case of this not blocking, then they are getting mixture on only C2 position. They are getting this sugar.
So without blocking, they are getting only at the C3 position, not the C2 one. But when C3 is blocked, then they are getting at the C2. Only one product is there, not the two.
Why not getting mixture when not blocking?
When not blocking, I think it's a normal. When mechanism is undergoing, the lone pair will go over here at the C2, like this bond. Then it will shift over the electrophile. It will attack on the electrophile. Then they are getting at the C3 position. So this is very general procedure. In the case of indole, we are getting only at the C3, I think, radioselective C3, not the C2, because of this nucleophilicity difference between C2 and C3 carbon.
Okay. And second thing, you go in mechanism.
Okay.
Here this HI is forming now.
Hydroiodic acid is forming in this case. Yes.
So this also can activate this disulfide or not?
They have shown only molecular iodine, but maybe it can also activate. There is no problem. Like
Because
this sulfur.
H plus go on one sulfur and HI go in another sulfur, like that.
Oh, you are telling like SH will form one SH and another one is SI. It can. No, yeah. Basically, this sulfur will attack, right? Sulfur will attack on the iodine. Then this bond will break, right?
Yeah.
But here it can be possible. It's not a problem, I think.
Because it is good, sulfur is good nucleophile, na? Like
yes, yes.
So acid is there. This HI is acid.
Yes.
That's why I'm asking.
And further again catalytic cycle will complete, and again this 2B will convert to same, and again this process will go like catalytic mechanism.
Okay, what they proven with oxygen, if we are not taking, then reaction is not going.
This thing they have proven actually. It is
okay. Good. Okay, thank you, Via.
Yes.
Yeah, nice presentation, Mahesh. I have one small question, that how this 2B molecule is formed.
Which one? This one?
This 2B is this C6-thio.
Okay, so first they have taken the methyl glucopyronoside.
Huh.
Basically,
No, no,
what
like,
they did, I don't know, but I am telling this route of the synthesis of this one, how generally preparing. First, methyl glucopyronoside, then
yeah,
protection with the, yes,
like means how C6 thio will
yes, I am telling that one thing.
okay, okay,
First, they are taking this methyl glucopyronoside, then they are protecting the C6SH, not
C6,
C6 with the trityl or something else group, and other
okay,
group they are protecting the benzoyl. Again, they
okay,
protecting deprotecting the C6OH. Okay,
okay, okay,
deprotection of the C6OH, and maybe there they are forming Br, and in thioacetic acid like ESH is there, COCH3.
okay,
So
okay,
thioacetic acid will attack on the Br, and there is formation of ES double bond COCH3, and
okay,
further they will deprotect that COCH3 like hydrogen condition or maybe in the acetyl chloride condition. So SH will form there. So this is the normal like method.
okay, okay,
Mm.
okay. Thank you.
Yes.
Nice presentation, Mahesh.
Yes.
I don't have any question. Just I am asking, like, if suppose in thio position, if we are keeping this peptide coupling, and then there is a possibility we can keep some group selectively at anomeric position. So later we can do the glycosylation also.
So thio position, there is some peptide here, and
Or
here there is some thio, you're telling.
thio,
Yes.
and later after doing, suppose making disaccharide, this
Okay.
thio we can convert it to this peptide things like using indole moiety. They haven't
Okay.
shown the disaccharide, right?
No, they haven't shown. They haven't shown.
Probably because whatever the target you have shown,
Hmm.
that it is present, it may not be like that. You go to the
Okay.
slide once.
This one you're telling, I think. Sugars. Okay, this one.
No, before this first slide. First slide you have shown, right? Some
Oh, okay. These alkaloids, different types of alkaloids. Yes.
slide are this. So everywhere. See this. Okay.
Mm-hmm. Glycosidic, diglycosidic. Basically, they are getting diglycosidic indole alkaloids also.
So these 3 and 4, this is different than whatever reactions you have shown, right? 5.
Yes.
Okay.
5 and 6 also, they are basically different, but they have tried one reaction with the C1 thio also. There also they are getting some good yield, but
There must be more examples will be there. There might be possibility there. So you can use some higher sugars or maybe on disaccharide also if you'll try. That may be useful, right?
yes.
Okay. So I think just it has to be compatible with those reaction conditions.
Reaction conditions. Yes.
Okay, good. I don't have question from the reactions.
Yes.
Thank you.
Nice presentation, Mahesh.
Yes.
I waited for you, but you didn't. Okay. So Mahesh, in the mechanism first.
Continue.
In the mechanism, yes.
So when you start with the 2B with the iodine I2,
Yes.
I think the product will form the 12. But since the necessity of acid will be more, so it will form disulfide.
Okay, they're starting from 2B, they're getting 11.
But before that, they will get, I think, 12, I think, right? Or
No, it is.
How is the 11
it,
will form?
actually, this one 11th reaction is very fast. This oxidation of the formation of disulfide bond. So
How it will
here,
form, like,
so here it is forming as a fast reaction in generally, but they have not mentioned any other experiment. So they are getting okay. So 11 is first or 12 is first. But there is one thing that this 11 is breaking into the 12. That things they have proven. That means either first this 12 will form, reaction will happen, and some compound of this 2B is going to the 11 also. And that will also again go to the 12.
Exactly. So 11 will form. Again, when
Yes.
they were taking the I2,
Yes.
it will come ultimately again to 12. Now,
12.
since there is no further aspect, so
Yes.
it will ultimately go to the like a product with the
Product formation.
Yes. Okay. Okay. Got it. More
Yes.
question I have, when they are using the peptide,
Huh.
so in that there will be tryptophan unit, like there will be chances of having the again this indolent ring.
There will be having what?
Indole rings. If the amino acid is tryptophan, something like that. Like if you consider the like peptide.
Okay, but they have not shown that example actually. Tryptophan, glycine, like different amino acid they have shown. You are telling there may be two tryptophans, then what will be the reaction, right?
Yes, yes, yes. But in case of peptide, for sure there will be one amino acid which is tryptophan residue.
Yes, yes.
They have not taken that example.
There is no such kind of example, but I think maybe if there are two tryptophans, then both the side reaction will happen. Like both tryptophans, there will be reaction. 1, 2.
Okay, man, that's all I have. Thank you.
Okay.
Nice presentation, Mahesh.
Yes.
So, one small, I think, if I am not wrong, while calling this indole position, it is not C3 position, it's a third position. If I am not wrong, I think so. We can't call it as a C3 position.
C3.
It's a third position of the indole, if I am not wrong.
Yes,
Like
yes.
anyway,
No. It is C3 only. It is this one is called as N1. Nitrogen is there, that's why N1. Then this one is carbon is there, so C2, and this one has a C3.
okay.
Because in the paper they have mentioned like this: N1, C2, and C3.
C3 position.
Yes, it is
Okay,
like
okay, okay,
mentioned.
okay. Then I must be wrong then. So, my question is like, can you go to that initial slide where you have showed your natural product?
Yes.
So here you can see all the product they have showed. I don't know why they showed the oxygen glycoside means other while they are going for thioglycoside, they have shown only two example of thioglycoside. That itself is I don't think so very much convenient. They should not show the other example of I don't know that glycoside. And go to the title slide.
Yes.
Right. You see here containing peptide with thioglycoside. In the whole paper, I didn't see a single thioglycoside, right? The
So basically that
C6SH can't be called as a thioglycoside.
for that they are telling it is under the thioglycoside. I also have the same question, but since in the paper they have mentioned that, so in the presentation I also mentioned. But thioglycoside, I was also thinking maybe C1 position thio is there, so that is called as a thioglycoside. If
True,
there
true,
is
true,
C1.
true. It's not about I'm asking you. You did that one. I'm telling the whole paper. I'm questioning the paper.
That I also same question got in the while reading the paper, that how it can be
Uh,
the thioglycoside.
and also, it can't be called as a thioglycosylation.
No,
I
it
don't
can't be
know
called
whether
as
we
that.
can call it as a thioglycosylation or not. Glycosylation is nothing but you should order something in C1 position of the this one, right?
Yes.
Whatever.
Not
Mm.
glycosylation.
Yes, no.
Uh,
So in the whole paper, the concept of title itself is not appealing. And the whole paper, they showed the initial example of anomeric thioglycoside, but the whole paper is about the C6 thioglycoside. Did they mention anywhere that they have tried with anomeric thiol, they didn't get
Yes,
the reaction or something?
one thiol they have tried, but I don't know why they have not increased the substrate scope with this one thiol. These three you can see, they
Okay,
have
okay,
tried this
okay.
reaction.
And that's
Uh,
good yield only.
only one example they have shown.
Okay, then I don't know why they went with the C6 thiol for the whole paper. Actually, I was preparing the slide for literature presentation. I was preparing this slide also. That time I was feeling that much like that. That time I felt this doubt how these people are doing all these things
Hmm.
and all. And
Yes,
as Deepak
yes,
Bhai was telling also, like as a general question I'm asking, like if you want to extend this glycoside, that
yes.
OME can be cleaved and either you can convert to any, I don't know, we can't just have, like I said, either TCA or somehow we can extend the sugar backbone, right?
Okay, so here will be peptide and another this
Uh,
backbone we can
uh,
extend like you are
uh,
telling.
uh, 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 uh.
Yes, yes, that can be happen. Yes.
So they didn't try that one as extension of sugar in its also.
No, no.
Different texture itself. Suppose we'll keep a lie Latin American position and
Hmm.
we can directly. I don't know.
Yes.
If some another donor means instead of OME, you can keep suppose OBZ only. Later you can make it
uh,
hemistellar.
uh, something orthogonal function group at anomeric position we can keep and use this one.
They have
Yes.
done very exemplar. They have stuck with the only one nucleophile.
Nucleophile.
I think I am
True, true.
thinking sometimes it is better also. Like maybe they are taking okay only one in the one paper and another thing they are exploring some other paper. I don't know, but people are doing like keeping the substrate like narrow thing.
Mm, mm,
So
mm.
targeting one target like something they are doing. I don't know.
So all this brings lot of questions. So what is this MW means in the reaction condition?
Microwave reactor. It is a
Oh, okay,
microwave
okay,
heating they are doing.
okay. So
Hmm.
you go to the substrate amino acid, different amino acid substrate scope table.
Yes.
Uh, uh, this one, right?
Hmm.
Okay. NSCBZ. Okay, they have tried a different peptides. But then still, I
Yes.
didn't. For me, while reading the paper, also, it didn't appeal too much as a research paper. That's what I felt. I don't know.
Hmm.
Like the concept itself is. Anyway, I don't know. The way we think is different. We do little target molecules. We see in a different pathway. Maybe the synthetic chemist is in a different pathway. Okay, that's fine. I think that's what I have questions. Okay, thank
Okay.
you.
Okay. Thanks.
Again, if possible.